So today we will see this lecture on resizing images. Actually, the question it is somehow disguised as resizing, but it is a more general question. It is image interpolation. So let's see the concept here. So let's say that you have an image. This is our image, and you know the values of the image in this location, or in the middle of the pixel. And now you want to evaluate the image somewhere else. So you want the value of the image here. So there, you strictly speaking, you don't know how what the image value is because you don't have any sample there. So somehow you will have to take a decision on which is the value there. So a sensible question, a sensible answer would be, okay, take the value from the nearest neighbor. So you go to here, and that will be nearest neighbor. Another sensible answer would be, okay, so take the 4 nearest neighbors. So these 4, and somehow take a value there, considering the 4 at the same time. This will be bilinear interpolation. And why not to extend to more samples? So why not green, I don't know, yellow? So why not taking a bigger neighborhood? Yeah, so saying that this image is bigger, so it's bigger, so we have more samples. So why not taking a bigger neighborhood and then estimating the value from all these samples to estimate this one? So all of them are taken into account, and this would be the bicubic interpolation. So this is what we will see today.
What was the name of the nearest neighbor 1 and the 4 nearest neighbors 1?
Bilinear. Bilinear. This one is bilinear.
This is the red one. The first one.
Red one is nearest neighbor. Here is. So if you want, these can be considered as Taylor expansions. The Taylor expansion, you know what it is. So this could be the Taylor expansion of order 0. This would be the Taylor expansion of order 1. And this would be the Taylor expansion of order 3. Okay. So let's see how to do this. Okay, so as I said, everything will be presented as a problem of resizing images, but actually the true problem, the true mathematical problem is not resizing the image, but it's interpolating the original image. Okay, so yeah, and as you can imagine, the different decisions that you take, which one you will use, will have an impact on what is the quality. So, for instance, let's say that you interpolate with 0 order this nearest neighbor interpolation, you would expect it to be of worse quality than the bicubic interpolation because you have a higher order approximation to the function. And that will be the case. Okay, good. So let's start by this nearest neighbor. So let's say that you have this small image and you want to enlarge it to produce a larger image. So let's say that this image is of size 10 times 10 pixels, and you want to produce something that is 4 times bigger. So it is 40 times 40 pixels. So how you would do that? So one possibility is, okay, I will start with an empty canvas. So I have my image of 40 times 40. Then I have here 10 times 10 pixels. So I will distribute them equally. So evenly spaced. So this one will be the first pixel, then the second pixel, the third pixel, and I leave 3 pixels in between. So it is 1 pixel, 3 pixels in between, 3 zeros, and then 1 pixel, and then 3 zeros, 1 pixel, 3 zeros, and so on. So I have enlarged by a factor 4, and now I have to fill the values in between. So filling the values in between, this is an enlargement of that idea. And then filling the values in between can be simply copying the one in the top left corner. Okay, so in each one of the blocks, you have to copy that value. So in this block, you copy that value. In this block, you copy that value. So that is what we will do here. So you are filling by simply copying the top left corner. So here, what we are doing is copying this nearest neighbor. Okay, good. Then this would be upsampling or enlarging the image by a factor of 10. Then we can do the opposite. So we have a big image and we want to reduce it by a factor of 4. So one possibility is, okay, so you take a zoom from the original image and then you take one every 4 pixels. So you take this one, this one, this one, the red ones, and simply you copy those values, and you will have the reduced image. This operation is called decimation, and this you already know from signal processing. It was represented this way. Okay, so you have a signal x of n, and then you have the decimation by a factor m, and then you were producing y of n. And you may remember this is n, this is x of n. Let me do y of n purple. So if you have your samples on this one, then the purple ones are these ones. So it is 0, 2. Okay, let me do it this way. So this would be 0, 1, 2, 3, 4, 5. So I did it wrong, right? This one is black, but this one is purple. So in the coordinate axis of x, this is the black one. So these are samples 0, 1, 2, and so on. But in the coordinate system of y, that has a different coordinate system, this n is not the same as this one. This is sample number 0, this is sample number 1, this is sample number 2. So you have done this decimation. This is called decimation. And the one that we saw before, the one of enlarging the image, would be the opposite. So it would be just the opposite. So you start with a signal. So n. You do the upsampling by a factor t or factor n, and let's do it again with variable n. So you would have a signal. Here it is less more difficult to draw on the same scale, so I will do it. Let's say that the rest are zeros. This is x of n, this is n, and now the purple one will be y of n, and that would be, this one stays, but then you have a 0. Let's say that my m is equal to. And then this one is copied, and then you have a 0, and then you have another copy, another 0, another copy, another 0, and so on. Okay, and another 0, this one, another 0, and so on. Okay, so what are the mathematical descriptions of these things? So decimation, this is called upsampling. This is called upsampling. And the decimation is simply this one. This is x of mn, and this one here y of n is x of n divided by n, if n is a multiple of n, 0 otherwise. Okay, so these operations you already know from one-dimensional signals. Okay, so we are doing just that. So now if you think of this one, so this is the decimation. So you are taking 1 every 4 pixels. So this is just the decimation. So you are taking those samples and then putting them together into a single image, into a single signal. And this one that we did, at least this operation here, this operation was just upsampling. So it was the upsampling that we presented. And then the filling is a convolution with sample, which you also know that typically you do. So it is now a convolution with this one, and then this one will be copying the signal. Okay. Very good. So now we understand this nearest neighbor interpolation as in concepts of decimation, upsampling, filtering that we already know. Okay, very good. So let's see some examples. So let's say that you want to reduce, so we have seen enlarging or reducing the images by integer factors, so by a factor 4. What if I want to do it by a fractional factor? So what if I want to do it by 3/7? So I want to construct an image that is smaller than the original, and it is of this size. So it is not a half or a fourth of the original, but a fraction of the original. So how to do that? So one possibility is, okay, this is the original image, then I want to reduce by a factor 3/7, so I divide the original image into blocks of 7 times 7 pixels. So, and then in these blocks, in each one of these blocks, I have to take 3 times 3 pixels. So this is one possibility. Any other possibility here would also serve the purpose. Okay, but then this scheme has a problem. You see the sampling is uneven. So between the distance between one sample and the next, here it is 1 pixel, while for these two, it is 2 pixels in between. So there is an uneven sampling of the original image. So, okay, nearest neighbor cannot do anything better. And this is what will result. But we know already that it has this problem of uneven sampling. And yeah, so this is just keeping those pixels and putting them together. And then we have that. And this is the final result. Okay, so very good. Okay, so then let's do the opposite. So now we want to enlarge the original image by a non-integer factor. So you have a small image, you want to make it bigger. So now we can do the opposite. So let's see, we have some nice drawing. I think this one is the nicest. So it would be the opposite. So you would divide the output canvas into blocks of 7 times 7 pixels, and then you would fill 3 of them. So this, you would take blocks of 3 times 3 from the original one, and you would spread these 3 times 3 blocks into the 7 times 7. And again, you have this uneven sampling. And you have some values, but what about the values in between? So all these values that are empty, then you have, you do the same strategy as we had before with the nearest neighbor. You simply copy the nearest pixel to them, and nearest in the sense of left and top. Okay, so these ones would be copying the left one. This in the middle of 4 would be copying this one, and the same here. This big area would be copying this one, and so on.
So what about in the borders? Like for example, like these up left borders.
Here in the borders, you don't have so much problems, no? Because the same strategy would simply copy the first one.
Okay, yeah.
And here it is the same, so you don't have to do anything special in the borders.
Yes.
Yeah, it is the same. But in general, it is true that when you do image processing, you have problems in the borders, but in this particular operation, you don't. Okay, so this would be the copying and final result on that. Okay, so in general, which is the value we should copy? And somehow, this is, I find it quite complicated. So this presentation, I find it complicated. Let's give it here a kind of same idea, but I think in a more simplified way. Okay, so let's say that we have an image of some size. So let's say we have some Y size, X size, and then we want a different size. So let's say we want Y prime, X prime. And this applies whether you are going to a larger image or to a smaller image. So in general, they will have different sizes. So now let's define a couple of factors. So these couple of factors will be Sx, that will be the ratio between X prime and X, and then Sy, that is the ratio between Y prime and Y, so the different sizes. Now, let's think of where each one of these pixels should go. Okay, so let's say that this is the 0, 0 corner, and this is the Y minus 1, X minus 1 corner. This is 0, and this will be X prime minus 1, Y prime minus 1. Okay, so now forget about this is true, okay, but I think the minus 1 complicates quite a lot the representation. Okay, so let's say that this is X and Y, X prime, Y prime. But it is true what I said, that it is minus 1, 1. Okay. But let's keep it simple with X prime, Y prime, X, I. Okay, so now we say a location here should go, so if you have this location here, it should go to R prime, and this R prime is Sx, Sy. Have so much space, right? So we will say it goes to R prime, that is Sx, 0, 0, Sy, R. So this is our transformation. So 0, 0 will go to 0, 0. And then xy, if I multiply by this factor, it will go to x prime. And y, if I multiply by this factor, will go to y prime. Okay. So this is given an input coordinate, how do I transfer that coordinate to the R prime space? Okay, so this is the key. So for every coordinate, you have to find a transformation that gives you then how that coordinate is transformed into the output space. And if you want it now, you can invert it. So let's say that I want to go from R prime. So let's copy it again. So let's copy it again. So R prime is SR, and S is that scaling matrix. So now if I want to solve for R, then you can say R is S minus 1 R prime. So when you go, let's put it here. So when you go in one direction, you apply the matrix S. When you go in the opposite direction, you apply the matrix S minus 1. And this is the R space, this is the R prime space. So this is the key of this lecture, that you need some way to transform coordinates from one space into the other. Okay, and in the case of scaling images, this scaling matrix is very simple. It's just these scaling factors, but you can construct more complicated coordinate transformations, and we will do it at the end.
And the matrix of like once you inverse the what is that like matrix?
The matrix, the inverse matrix of that one. Okay, so this is S. So let's say that S is Sx 0, 0, Sy, then S minus 1. In this particular case, it's 1 over Sx 0, 0, 1 over Sy. In that particular case. Okay, very good. So this is what is explained here. So all the minus ones comes from this from what I said, that the last pixel is x minus 1 or number of columns minus 1 or so on. But it complicates quite a lot the presentation. So in general, let's keep it simple. Let's say that the scaling factors are simply the ratios between the two sizes. So now it comes this idea. Okay, so now I know how to transform coordinates from one space into the other. But in general, these transformed coordinates will be fractional numbers. And I don't have the pixel value at that fractional number. So this F stands for a fractional. So I have to do something with those fractional coordinates, and the nearest neighbor strategy is to simply round them. And now once you round them, you will have integer coordinates. And now you know the value of I at those integer coordinates. So you simply copy that value. Okay, so everything that we have presented here, which seems pretty reasonable, is simply applying this rule. So everything that we have seen so far can be summarized here. So there is some scaling of the coordinates to transform from one space into the other. That will give you fractional coordinates. Then you round them, and that is the nearest neighbor. And then you simply copy that value. Very good. Yeah. So yeah, this is now he has a lot of slides to present the same idea, but they are not. Okay, so here you have the idea of fractional coordinates. So the 0, 0 is not goes to an integer location. So the 0, 0, when I multiply by the scaling matrix, it stays at 0, 0. But the next pixel, because of the fractional nature of the scaling factor, it will not be at the middle of a pixel. It will be somewhere else, and I'm simply copying. Okay, good. Yeah, and the same if you are, so this is if I am reducing the image This is if I am enlarging the image. So now, again, I have fractional coordinates, and these fractional coordinates, I don't have the value there, so I have to round. So this value will be rounded to this one. This value will be rounded in this one too. Very good. Yeah, and this guy cares a lot about the borders and so on, but we don't care so much. So the main idea here, so all these slides you can forget. So the main idea here is that this coordinate that we set here, in general will be fractional, and then you have somehow, actually, this is interesting. So most often, so now we know how to go from one space to the other. So this is the input. Traditionally, we have named this one as I, this one as J. So the input, J is what you want to produce. So even if this relationship is true, this is true, but that is true, and this is also true. And then we normally go this way. So for every pixel here, you see where it is coming from, and then you simply copy the value there. Okay, so always, this is a very common strategy in image processing. You go from the output always to the input, because the input everywhere in these integer locations, but you know them everywhere. So you always go in this direction to see which pixel I have to copy. Yeah, this is still fractional, but yeah. Well, this is fractional too. So this one is fractional, this one is also fractional. Sorry? Because otherwise, if you go in this direction, sometimes you have empty spaces. So this pixel goes to one. So let's say that, let's do it this way. So then I want to copy, okay, and I want to go in the other direction. So go into this direction, and then sometimes the first one goes to the first, the second goes to the second, but then the third one goes to this one, and then you are leaving an empty pixel there. Okay, good. Then the next part of the lecture is, okay, what if instead of copying, I try to do something more clever that will be this bilinear interpolation. This bilinear interpolation, we introduced it at the beginning. It was this idea of, instead of just taking the nearest neighbor, just take the 4 neighbors around, and then somehow with these 4 values, try to guess what the value there should be. Okay, then let's do that. So here you already see what will be the difference. So the difference with nearest neighbor is that you have kind of this line somehow when you enlarge, so this line, when you enlarge it, you have this kind of stairs, while this one is smoother. You still have some kind of juggling, but not so much. Okay, good. So yeah, this is the result with simply copying. So you put the pixel, and then you copy all the ones around. And this is the result with bilinear interpolation. So for every, remind that we are always going in the other direction. So from here, we are going into the input image to see which value that is. So with nearest neighbor, we are always copying the same value. With bilinear interpolation, we are taking kind of gradient. So this one is white, this one is darker, and then we have all the values in between. So that is what we will do. Okay, so let's say that I want, so let's say that I want to evaluate the pixel here in between. Okay, so I have these 4 pixels I know, and I want to evaluate the pixel here or there or there or there. Okay, so how can I do that? So I want something kind of in between, and the trick will be yeah, so somehow it is represented here. It is not a very faithful representation of what is happening. So, but somehow it helps. So we are not fitting a plane. So there is, it is not, we are calculating the plane that goes through these 4 values. So what we are doing is, and that is why it is called bilinear. So we are fitting a line here, we are fitting a line there, and then we are fitting, yeah, this line, and now for the point that you are interested in, you draw this line and this line, and then you compute the intersection of those lines.
Like a couple of gradients.
Not a couple of gradients, but it is fitting lines. So gradient has to do with the derivative, and yeah, if you want it, you could compute the slopes of these lines, and those would be the gradients. Yeah, the slope of the lines are the gradients. That is true. And so it is, the process is, I fit this line, I fit this line, I fit this line, I fit this line, and then for that point, I cross those 2 lines and I evaluate the value there. Okay, so let's do that. And then, for instance, here, so this one is for the one in the middle, but the borders are easier because in the borders I have a single line, so I have simply to evaluate that line at that location, to evaluate the line at that location, and so on. Okay, so let's do that. So yeah, let's take that image. We will go into the mathematics later, but let's take this image and let's enlarge it by factor 4. So let's look at this parallel side. So this is the bilinear interpolation. Okay, so this is the result of the bilinear interpolation, and then what you do is the same process I described. So first you fill the space 1 every 4 pixels, and then for each one of them you are fitting a line here in these 4 pixels, and then evaluating those lines in all the pixels in between. Okay, this is the result, and somehow, yeah. So this is the result, I think. So all these ones here, somehow they are the nearest neighbor representation. And so this is nearest neighbor interpolation. This one is bilinear interpolation. So you see this is a smooth transition between one and the next, one pixel and the next. This is nearest neighbor. This is bilinear interpolation. You can see, for instance, the difference between the two. So this one is much smoother. All the boundaries are much smoother. Same representation. And now we can do that with this fractional resizing that we were doing before with the nearest neighbor interpolation. So this was the problem that nearest neighbor interpolation had, that it had somehow this uneven sampling, but now with the bilinear interpolation, we have a regular sampling. So the distance between every red dot, that is, those are the fractional coordinates. Now all those fractional coordinates, we can evaluate them with bilinear interpolation, because with bilinear interpolation, for instance, this red pixel here, I can take the 4 values around and I can evaluate the value in between. Okay, so here we have them. And so for this pixel here, I can evaluate what is the value between these 4 values, for this one 2, for this one 2, and so on. Really good. So then let's do that for one of those. So this is in general the problem. So in general, you want to evaluate the red pixel in this location, which is fractional, because these are the ones that are have integer coordinates. So in general, I want to evaluate the function there, there. So those are different examples. All this is this. This guy is rather repetitive. So let's go to the interesting stuff, that is this one. Okay, so in general, you want to evaluate the function there when you know how, so these are fractional coordinates, and you know the 4 pixels around. And if these are fractional coordinates and the rounding down of this fractional is RC. So let's give some numbers so that you don't get lost with the notation. So let's say so say that this is pixel, I don't know, 127. 127,63. This is the coordinate of that one. This will be 127,64. This will be 128,63, and this will be 128,64. And I want the pixel value here. So that one is 127,7, then 64.6. Okay, so these are the fractional coordinates where I want to evaluate, and then this is simply the rounding down. So sorry, this is 63. This is 63. So this is the rounding down. So rounding down 127,7 is just 127, I think the same before. Okay, good. So in general, we have RC, R, C plus 1, R plus 1C, R plus 1, C plus 1. Okay, now I will call these comma 7 or comma 6 that we have, I will call it delta C, delta R. And then if this is delta C, this is 1 minus delta C. And if this is delta R, this is 1 minus delta R. So I will, what I said before of fitting the lines is true. So this is the process of fitting the lines, but fitting the lines is a complicated process. This one is much simpler. And let's see if this simpler process, which is, so fitting the lines and doing this is exactly the same. The formula is exactly the same. But if we give directly the result, probably it makes a lot of sense. Okay, so let's see. We will take the 4 pixels, and each one of the 4 pixels we will multiply by a quantity. And this quantity depends on how far you are from that pixel. So let's say that I am very, very close to RC. So if I am very close to RC, probably what I want is that RC has a lot of weight, and these 3 other pixels, they don't have so much weight. So if I'm very close to RC, let's say that I am on RC. So if I'm on RC, delta C are zero. So I have IRC, then this is zero. This is one, sorry. This is one, this is one, but this is zero, this is zero, this is zero. So that means that if I am here, only this one contributes to the final result. What if I am there? If I am there, then delta C is 1, delta R is 0. So delta R is, so delta C is 1. So if delta C is 1, this is 0, this is 0, this is 1, and this is 0 again. So only RC plus 1, that is this one, contributes. So you see that, and for any combination that you take, it is the same. So if you are closer to this pixel, that pixel is the one that contributes, all the others contributes less. And these things are the areas of these squares. So now to take this square, this square, this square, and this square. So how much you contribute is somehow the complement, or somehow is related to those areas, but it is not. So IRC doesn't contribute with this area, but contributes with this one. And this pixel doesn't contribute with this area, but with this one. So is it clear, or you need? It is a weighted mean. It is a weighted mean. And the weight depends on how far you are from that pixel. Let's do it. Let's do it with colors. So let's say that, let's say, 4 pixels, and we call it, this is our seed, this is delta R, and this one is delta C. So this pixel will contribute with this area. What is this area? It is 1 minus delta R minus 1 minus delta C. And this pixel here will contribute with this area. If I'm not mistaken, this is delta R minus 1 minus delta C. So, okay. So this is the R plus RC plus 1 pixel. So the RC plus 1 pixel, RC plus 1 contributes with 1 minus delta R delta C. Is that what I want? Okay. Very good. Yeah, and this is the explanation of that process. Okay. And this is so all this part is the same. So all this part is the same as I described before. So we have some transformation matrix to transform to get the fractional coordinate you want to evaluate, and then you have you take that fractional coordinate, you round it down, you get RC, and now you apply this bilinear interpolation to RC. Actually, the Wikipedia representation of the bilinear interpolation is pretty good. See, this is Wikipedia. Yeah. Okay. Yeah, so you have the same kind of coloring and this thing that I said. So you feed a line, you feed another line, you feed a line here, and you evaluate that line in this location. Okay. And the process is the same if you feed the horizontal line, so you feed, so it will keep the same value. Yeah, and then this is, okay, so bilinear is just this one. And so it is what we described. So feed a line, feed another line. You evaluate the x of the location that you want, and then that line that you feed there, the purple one, you evaluate that y. And the cubic will be doing this. So for every line, so for every set of pixels, you will be feeding a cubic polynomial. And this one, you will be feeding another bicubic polynomial, this one, another bicubic, another bicubic. And then each one of the polynomials you evaluate at x. So you evaluate at x, and this will give you these 4 points. And then these 4 points, you feed another polynomial, a cubic polynomial, and then you evaluate at y. And the difference between these two processes is somehow you're approximating the underlying image by zero order Taylor approximation, first order Taylor approximation, third order Taylor approximation. So you're taking into account the derivatives of the underlying signal, and then your image, your interpolation will be even better. So this one. I will be smoother. Yeah. So yeah, this is one image, and then that image interpolated to different fractional levels. And then the same process, but now illustrated with color images. So actually you apply that process, and the pixel value of that location. So the pixel value of that location. So here, I can be a vector. So I is a vector. So what we are doing is each one of the vectors you are multiplying by the value of that unit. And then you can do it with bicubic interpolation. And again, here I don't want to get very technical. What I want to say is that, okay, you have this process. I want the value at some fractional coordinate, and then this fractional coordinate I find, which is the RC, so that is the rounding down of that fractional coordinate. I construct all these ones, so on this grid. And then somehow I use all the values here, not only to estimate what the I function is, but also what the derivatives are. So the derivative in terms of columns, in terms of rows, and the second derivative with respect to columns and rows. And then here he's giving some formulas, but we will not pay attention to the formulas. Okay. But you get the idea here. So if I want to estimate what is the derivative of this function here, I need these two values to estimate the derivative in x, the derivative in y, and here I would take the similar ones. So the more values you have, you are able to estimate the function and its derivatives, and you can do it even bigger and go as far away from the fractional coordinate you want to interpolate as you would like. The more derivatives you would be able to estimate. But there is a compromise between the computational cost of doing all these calculations. You can imagine nearest neighbor, how many calculations you need to do with nearest neighbor. So this zero calculation, I simply copy a value. With this one, how many calculations do I need to do? So for every pixel, I have to make these 4 multiplications. So these 4 multiplications. Now, if you become cubic, now you have 16 values. So it is 4 times more expensive than bilinear interpolation. So the bigger you take the area around, you will be able to approximate the function better because you can estimate more derivatives, but it is more and more expensive. So typically you never go beyond cubic. that was what I wanted to highlight from here. So there are now, you see, it has the same kind of structure that we had before. So the value of the output pixel in some location is a sum of all the pixels around. So this sum is taking the neighborhood around. Each one of those will contribute with something that depends on a polynomial of the delta C, delta R. They depend on delta C, delta R. And this polynomial in B cubic, they are cubic polynomials. In bilinear, we have them here. They are linear polynomials, right? It's the same structure. The sum over all pixels around, and then the multiplication of two polynomials of degree 1 here, and in the B cubic, they are of degree 3. But the cubic formulas, they are not so important for us. So what we want to know is that these things exist. And then you can compare all kinds of results. Okay, so that is the original. We want to reduce the image by nearest neighbor, bilinear, bicubic. And then you can see the one that preserves the structure of the original image is the one of bicubic. So here you still see the windows as they were, smaller, but you still see the windows there in the right. But here in bilinear, you have some kind of pattern going down, and here it is even stronger. So that stronger thing is interpolation. Is aliasing. We haven't seen the concept of aliasing with images because we had to skip many of the lectures in between because the course was reduced by factor 2. But the same aliasing that you know from 1D signals, it also happens into the images. And this is aliasing. And it is aliasing because the interpolation, that is this nearest neighbor, somehow the anti-aliasing filter is not that good. And this one, the anti-aliasing equivalent anti-aliasing filter is much better. Okay, so here you have the original, here you have the nearest neighbor, and you see all these patterns here that are aliasing. And then bilinear, bicubic. So you see you have less and less aliasing. And then farther you go with farther higher order polynomials, you could go to you could remove completely the aliasing. And this is in the opposite direction. So now you are enlarging, and again the quality here. Now you don't have aliasing because when you are going up, you cannot have aliasing. But the quality of bilinear is better than the quality of the nearest neighbor, and the quality of bicubic is even better. And that's it. Any question? Yeah.
So when you do, for example, the reduction, and you take
When you do this?
the reduction,
Uh-huh.
you take the new 3 pixels, for example, in the second, what was it?
Bilinear.
Yeah, the linear. Those 3, like 3, 4, 3 pixels, you modify each value with the response.
Yeah. So the thing is that it was well represented. So because of the scaling, you would like to know what is the values at those red locations. But those red locations, they have fractional coordinates.
Okay.
And then you don't have the image at these red fractional coordinates. They have them in these 4 places where they have integer coordinates. And then what we have seen with the bilinear is how from the integer coordinates, I can estimate what the value of the fractional coordinate is.
Okay. And you have like 4 pixels in the, or the same pixels in the reduced image.
No, in the reduced image, you have fewer pixels.
You have, sorry. I get confused with the eye of the eagle,
Yeah.
because it looks like.
I don't remember what it is. Here, this one, yeah. Yeah, because what we are doing here is you make it smaller, and then just for the representation in the slides, you make it bigger again,
Yeah.
so that you can see the differences. Okay, so this one is copying all these values. This one is interpolating in between.
Okay.
So we have made a big zoom. So let's say that you reduce by a factor 4, a factor whatever, and then that reduced image, you make it bigger again so that you can see the eye closer. You have fewer pixels than the original one.
Yeah.
So in the original one, let's say that you have 1,000 pixels, 1,000 times 1,000,
Yeah.
then you make it smaller, 250, 250. But for the representation here, I make it bigger again.
Ah,
And then in this enlargement, it is where I am replicating the values or interpolating the values. More questions? No? Okay, so